Good morning, dear students. Welcome back to physics class. Today, I would like to discuss on mainly two topics. They are A. Heat, work and internal energy, and B. First law of thermodynamics and its related numerical. In today's class, first I am going to point out thermodynamic state variables. You have to understand that thermodynamics deals with the relationship of heat energy to mechanical work and other forms of energy. When we rub our palms, they become warm. This is due to the conversion of mechanical work performed in rubbing our hands together into heat energy. Thermodynamics deals with macroscopic properties and does not go into microscopic level. So, thermodynamic state variables are the macroscopic quantities which determine the thermodynamic equilibrium state of a system. These macroscopic quantities are known as thermodynamics state variables. They are mainly pressure, volume, temperature, mass and composition that are obvious to our senses and are measurable. There is one more macroscopic variable. It is internal energy, which we will study in upcoming session. These variables can tell us the position or the condition of any gas at that particular instant of time. You should remember that since these macroscopic quantities describe the behavior of thermodynamic system, they are known as thermodynamics variables. Since they determine state of a system at one particular time, they are also known as thermodynamics state variables. In thermodynamics, there are two more variables which may involve but they are not felt by our sense perceptions. That is, they are not obvious to our senses. They are entropy and enthalpy. What is entropy? Entropy is measure of thermal energy of a system per unit temperature, which is not able to be used for doing useful work. It is thermodynamic work, which is done by ordered molecular motion in a system. So, it is measure of disorderliness or randomness in a system. Then, what is enthalpy? It is measure of total heat content of a system. These all are macroscopic variables. However, a thermodynamic state in general is specified by 5 state variables. They are pressure, volume, temperature, internal energy and entropy. It is important to note that a system not in equilibrium cannot be described by state variables, which means that macroscopic variables are changing with respect to time. That is, they are not constant. The figure A shows the partition in a box is suddenly removed, which leads to free expansion of the gas. And figure B shows a mixture of gases undergoing an explosive chemical reaction. In both situations, the gas is not in equilibrium and cannot be described by state variables. Now I am going to discuss on the concept of internal energy, and its connected topics are heat and work. What is internal energy? Internal energy depends only on state of a system. Since every system consists of a large number of molecules, it will be equal to sum of kinetic energies and potential energies of the molecules constituting the system as a whole, and not of individual molecule. Internal kinetic energy depends on temperature and internal potential energy depends on volume. Internal energy is a macroscopic variable of a system, which is a thermodynamic state variable. It is denoted by capital letter U. It is specified by values of pressure, volume, and temperature at that particular time. In figure A shows a box at rest, then the internal energy of the gas inside the box is sum of both potential and kinetic energies of its molecules. And in figure B, if the same box is pushed with some force and it starts moving as a whole with some velocity, then the kinetic energy of the system is not directly added or it is not included in the internal energy U. Why? Because the system is not in equilibrium. There are two different modes to change internal energy. They are heat and work. Let us take a bottle. A balloon is tied at the neck of the bottle. When we heat the bottle, due to the difference in temperature, heat flow takes place. As a result, balloon blows up. There is a transfer of heat energy. This results in change of internal energy. And work is to be done by the system. We can do some work on the system. In this case, system is bottle with a balloon tied. Here, by pressing the blown balloon, work is to be done on the system. As a result, the internal energy of the system changes. Internal energy increases when the system absorbs heat energy and some work is done by the system, and internal energy decreases if we change the conditions. To understand it more clearly, let us consider a cylinder filled with gas. Suppose it is to put in contact with a body at a higher temperature than that of this enclosed gas. The temperature difference will cause a flow of the heat energy from the hotter body to the gas, which results in increasing the internal energy of the gas. And the second way is to push the piston of the cylinder down. Here, work is to be done on the system, which again results in increasing the internal energy of the gas. This means that work and heat energy are two different modes of changing the internal energy. The remainder is heat and work are two distinct modes of energy transfer to a system that results in change in its internal energy. Heat is energy transfer due to temperature difference between the system and the surroundings, and work is energy transfer brought about by physical means. Example, by moving the piston of cylinder of gas by some weight connected to it that do not involve such a temperature difference. How is internal energy different from work and heat? Heat and work are not state variables unlike internal energy. They are two different modes of energy transfer to given system resulting in change of its internal energy. Let's learn about first law of thermodynamics. The first law of thermodynamics is same as law of conservation of energy. It is known to you. What is law of conservation of energy? According to it, energy can neither be created nor be destroyed, which can transform from one form to another form. When certain amount of heat energy is given to a system, a part of it is used to increase the internal energy of the system, and remaining part is used in doing external work. It is the work done by the system. According to first law of thermodynamics, the change in internal energy of a closed system is equal to amount of heat energy supplied to the system minus the amount of work done by the system on its surroundings. How can it express mathematically? It can be written as delta U is equal to delta Q minus delta W, which is the expression 1, where delta Q be the heat energy supplied to the system by the surrounding, delta W be the work done by the system on the surroundings, and delta U be the change in its internal energy. Here, some part of heat energy supplied is the work done on the surrounding, and remain part is used up by the system to increase or change its internal energy. Then delta Q is equal to delta U plus delta W. Consider a system whose initial state is P1 V1 and final state is P2 V2. Let delta U be the change in the energy of the system to change its state from initial to final state. The important thing about internal energy is that it depends only on the state of the system, which do not depend on how that state was achieved. It is a state variable, which means it is path independent. So its value depends only on given state of the system and not on history, that is, not on the path taken to arrive at that state. But work done and heat energy both are path dependent. It depends on how the path changes from initial to final. Therefore, the thermodynamic equation delta Q minus delta W is equal to delta U, where delta Q and delta W are the path dependent quantities, whereas delta U is path independent quantity. This concludes delta Q minus delta W is path independent quantity. How can we apply first law of thermodynamics in an isolated system? In case of an isolated system, there is no interaction of the system with surroundings. So, no work is done by or on the system. That is, delta W is equal to 0. As there is no interaction of the system with surroundings, then delta Q is also is equal to 0. By first law of thermodynamics, delta Q minus delta W is equal to delta U, as delta Q is equal to delta W is equal to 0, then delta U is equal to 0. So we can say that U will be a constant. Then the internal energy of an isolated system is always constant. When heat energy supplied is completely converted into work without changing the temperature of the system, the internal energy of the system will remain unchanged. Let us see two different cases. Case 1. When system undergoes a process such that delta U is equal to 0, which means internal energy is a constant, then by applying first law of thermodynamics, delta Q is equal to delta U plus delta W. By putting delta U is equal to 0, then delta Q is equal to delta W. This means that heat energy supplied by the surrounding is equal to work done by the system on the surrounding. And case 2 is, consider a system which is a gas filled in a cylinder with a movable piston. By moving the piston, we can change the volume of the gas. If we move the piston downwards, some work is done against the system. Here, volume of the gas is decreased. Then what should be the work done? Let it be delta W, which is equal to force into displacement. Since pressure is equal to force per unit area, then force F is equal to pressure into area. So delta W is equal to pressure into area into displacement. As area is multiplied by displacement equal to the change in volume of the gas, it is the decrease in volume of the gas, then delta W is equal to pressure into decrease in the volume of the gas. It is equal to P delta V, which is the expression 2. Therefore, by first law of thermodynamics, delta Q will be equal to delta U plus P delta V, which is the expression 3. It is the modified form of the thermodynamic equation delta Q is equal to delta U plus delta W. Here we have substituted the value of delta W, which is P delta V, in the expression 1. Let us discuss on types of thermodynamic state variables. There are two types of thermodynamic state variables. They are extensive and intensive variables. First, for extensive variables. Extensive property indicates size of a system, which means extensive variables are those that depend on mass of a system or number of particles in given system. Examples of extensive variables are volume, mass, internal energy, etc. If we consider a system whose mass is greater, then size of that system is greater. Then the value of extensive variable is higher, since they depend on the size of the system. What are intensive variables? Intensive variables are those which do not depend on size of system. They do not change when you take away some of the sample given, whereas an extensive property will change. Examples of intensive variables are pressure and temperature. How can you decide which variable is extensive and which variable is intensive in a given system? Consider a relevant system which is in equilibrium and suppose that it is divided into two equal parts. Those variables that remain unchanged for each part are intensive variables, and those variables whose values get halved in each part are called extensive variables. You know that internal energy, volume, total mass, etc. are extensive variables, and pressure, temperature, and density are intensive variables. It is a good practice to check the consistency of thermodynamic equations using this classification of variables. For example, in given thermodynamic equation, delta Q is equal to delta U plus P delta V. The physical quantities on both sides of the equation are extensive. As product of an intensive and extensive variables is always an extensive variable. So, the product of P and delta V is an extensive variable. So, the physical quantities on both sides of given thermodynamic equations are extensive. Next term you have to know is equation of state. What is equation of state? Equation of state is that which depicts the relationship between the state variables such as pressure, mass, volume, density, etc. It describes about state of matter under given set of physical conditions. Consider an ideal gas equation of state which is PV is equal to nu RT, where P, V and T are state variables and nu is number of moles of given gas molecules. For a fixed amount of gas, we can have two independent variables, either volume and temperature or volume and pressure. All the variables cannot be independent at same time. This is highlighted by the idea of both Boyle's law and Charles' law. That is, we should use three state variables. Among these three, two are to be dependent one with another by keeping third one is to be constant. This specified equation is known as equation of state for ideal gas. Let's see the related numerical. First question is, when heat energy of 2000 joules is supplied to a gas, the external work done by the gas is 500 joules. What is the increase in its internal energy? Solution is, given that heat supplied delta Q is equal to 2000 joules. External work done delta W is equal to 500 joules. We have to find increase in internal energy. According to first law of thermodynamics, delta Q is equal to delta U plus delta W, then delta U is equal to delta Q minus delta W, which is equal to 1500 joules. Second question is, find the external work done by the system in kilocalories when 20 kilocalories of heat is supplied to a system so that its internal energy is 8400 joules. Given that heat supplied delta Q is equal to 20 kilocalories and internal energy delta U is equal to 8400 joules. We know that 1 calorie is equal to 4.2 joules. Then 1 kilocalorie is equal to 4200 joules. So 1 joule is equal to 1 by 4200 kilocalories. Then delta Q is equal to 8400 joules. When it converts into kilocalories, it is equal to 8400 by 4200 kilocalories is equal to 2 kilocalories. By applying first law of thermodynamics, we have delta Q is equal to delta U plus delta W. By substituting the values of delta Q and delta U, we get delta W is equal to 18 kilocalories. And third question is, an electric heater supplies heat to a system at a rate of 100 watts. If system performs work at a rate of 75 joules per second, at what rate is the internal energy increasing? Solution is, given that heat supplied to the system at a rate of 100 watts, then heat supplied delta Q is equal to 100 joules per second, since 1 watt is equal to 1 joule per second. The system performs at a rate of 75 joules per second. So, work done W is equal to 75 joules in unit time 1 second. From first law of thermodynamics, we have delta Q is equal to delta U plus delta W. Then delta U is equal to delta Q minus delta W. By substituting the values of delta Q and delta W, we get delta U is equal to 25 joules per second, that is 25 watts. Therefore, the internal energy of the given electric heater increases at a rate of 25 watts. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.